Hey everyone, I'm going to go over notes for 1.2, notes on limits. So let me just first start off by um, talking about the definition. So definition of a limit is the y value that a graph or function approaches as we move closer to a specific x value. Okay. Uh, Now something that is related to it that is also has some distinct differences, but also something that we recognize from algebra and from just graphing in general is finding function value. So finding function value is the location of the y value of the graph at a specific x value. Okay. So let's start off with something that we recognize how to do, which is function value. So function value is just where is the physical point on the graph. Okay. So let's say we have the graph here. This is r of x. We see there's a hole, and we see there's a location for that point that is in a different location than where that hole is. Okay. So this question, or this problem here, example, is asking what is the x value of the graph when x is equal to 2? And it says the y value of the graph when x equals to 2 is 1. So that's an equal sign here. And we see that's the case, right? The point at 2 is 1. That's the y value. That's the physical point on the graph. And the way that we would write this in function notation is we would say r of 2 is equal to 1. Because the graph exists here and not at this hole. All right, so we know how to do function notation. We know how to find the physical point on the graph. Given an x value, what is the y value location? All right. Now, limit is similar, but also there are some distinct differences. Okay. Now, the limit is not talking about necessarily the location at that specific x value. It's the approach, and that's something that we have to get used to. So the limit of the function r of x as x approaches 2 is actually 4. So we see that at x equals 2, the point is 2, but the limit is actually going to exist where that hole is. Okay. So in order for us to find a limit, the graph must approach the same real number y value from both sides of that target x value. So we're talking about the approach. So this is how I want us to think about limits. If we're trying to find a limit as x approaches 2, okay, we want to pick points close to 2 on either side of the graph. Okay. So I'm just going to pick a point that is relatively close to x equals 2 on the graph. So I'll pick a point to the left of 2, and then I'll pick a point to the right of 2. Now, I'm going to make my way towards x equals 2. And we see that if I follow the path of the graph on this side, it's taking me to a y value of 4. If I choose a point on the other side of the graph and I also move towards x equals 2, it's also taking me to the same y value. Even though this point doesn't exist, the approach is consistent, right? From the left side of 2, the graph is moving me towards 4. On the other side of 2, the graph is also moving me towards the same point. So as long as the approach is consistently moving towards the same y value, that is enough for us to locate that as the answer for our limit. So the way that we write this in limit notation is we say the limit of r of x as x approaches 2 is equal to 4. So that's the way that we write it. The function goes here, limit notation goes here. The approach, the x value destination that we're moving towards is here, and then the y value, where the consistent y value approach from both sides is sits in this location. Okay. Something I want to remind us is that the way that a lot of times we say the way that we represent limit in terms of how we say the limit as x approaches 2 is equal to 4. A lot of times we leave out the function, and because of that, it may lead to wrong notation. So this is how I see a lot of students write limit notation. Even though a lot of times we say limit as x approaches 2 is equal to 4, we're missing that function. We have to either represent an expression here, or we label a function name like how we did here. So make sure that we don't write it without that function indicated in some form or another. Okay. So again, in order for a limit to exist, the graph must approach the same real number from both sides of that target x value. So even though that point doesn't exist, the approach is moving towards that same y value. Okay. So now, here are some examples where the limit does not exist. Okay. So if the definition of a limit is approaching the same real number from both sides, that means a limit does not exist if the graph doesn't approach the same y value real number from both sides. Okay, if there's an inconsistent behavior from either side of our of the graph, then that is when we can say the limit doesn't exist. So for instance, in this graph, there's a jump discontinuity, right? We see that there are two branches. These branches are obviously disconnected. So looking at this graph here, the limit as x approaches 5. So we're going to approach 5 from both sides of the graph. So I'm going to pick points on either side of 5, and I'm going to move towards 5. So as I move towards 5, we see that from the left, it's taking me towards this location, and that is a y value of 2, okay? How about from the other side? From the other side, as we move towards 5, we see it's moving to a different location, right? So from this side is moving us towards 2, from the other side is moving us towards 1. We don't have a consistent movement or a destination from both sides. So even though the point exists here, and even though there's a hole there, the approach is not towards the same y value. So hopefully you guys see the distinction right here. The graph is moving towards the same y value, so that's why the limit exists. Here, the graph does not move towards the same y value destination, so therefore limit does not exist. And I'm going to represent does not exist as D and E, so that we don't have to write out does not exist every time. Okay. Now let's look at example 3 here. As we approach 3, we see that there's a vertical asymptote, okay? And just like how before, if we want to find the limit, we're going to pick points on either side of 3, relatively close to it, and we're going to move towards 3 in terms of following the path of the graph. So if we follow the path of the graph, this side is taking me towards a y value of positive infinity. And then from the other side, it's also taking me to positive infinity. So in a sense, isn't that moving us towards the same y value? But here's the thing. The thing is that it needs to approach the same real number y value. And infinity is not a real number. Even though it is technically moving towards the same y value, it is not a real number. So anytime we're approaching a vertical asymptote, we say the limit does not exist. Or you can say D and E. However, what we're going to do is, for these types of problems, we're going to go a little deeper than this. We're going to explain why it doesn't exist. And the why it doesn't exist is because both sides are moving towards positive infinity. So a lot of times we will say it does not exist, and then in parentheses, we'll say positive infinity as an indication of the behavior of the graph. We're kind of describing the behavior of the graph. Movement is towards positive infinity. So this is kind of a subcategory of does not exist. It does not exist because it moves towards positive infinity. And this last example, this is a graph with oscillating behavior. We're not going to see many types of this, but just to just to kind of show students here that for this type of graph, this oscillating graph sine of 1 over x, it looks like a jumbled mess at 3. And no matter how we zoom in, if we keep zooming in, the graph is not going to consistently move towards the same y value. It is a jumbled mess here. So here we say, anytime there's a graph with oscillating behavior, the limit also does not exist, because there's not a consistent movement towards a specific y value that we can identify. Okay, just some additional notes here that I want to point out is if there is some sort of a break in the graph, okay, such as a hole, a non-removable discontinuity, a jump discontinuity, a vertical asymptote, we can guarantee that our limit and function value will always disagree with each other, will always be different from each other. So if you see a break in the graph in a hole or asymptote or two separate branches, that's a red flag for us to indicate and for us to remember that limit and function value will not be in agreement with each other. Now, if the graph is continuous, if there's no breaks in the graph, it's a nice smooth curve, there are no holes, there's no asymptotes, there's no jumps, then your limit and your function value will be one and the same. You're not going to see distinction between limit and function value unless there's some sort of a break in the graph. All right, last example here on this page. Let's say we're using a table of values, okay? So let's say we don't have the graph in front of us. We just have a table of values, x cubed minus 1 over x minus 1. So here, imagine that we had this graph in front of us, right? We were picking 2 points on either side of the target. In this case, our target is 1. And from the left side of 1, we're going to start at 0.9, and we're going to move towards 0.9, or we're going to move towards 1. So as we move towards 1, look at the y value. What is the y value inching towards? 2.7, 2.97, 2.997. We see that it's inching towards a y value of 3. Okay. And just like with definition of limits, let's look at the other side, see if there's a consistent approach to the same real number y value. So we see the left side is moving towards 3. What if we chose a point on the other side of the target x value, and let's say we start at 1.1, and we move towards 1. And as we move towards 1, let's look at the y value. The y value starts at 3.31, then 3.03, then 3.003. And we can obviously see that this is inching closer towards real number value 3. Left side is approaching y value 3. The right side is also approaching y value 3. Even though the y value graph doesn't exist at 1, there is a consistent approach, and the consistent approach is enough for us to indicate that the limit must be equal to 3.